Welcome back to the Math Professors. If you like videos that cover topics that can be found in any college math class, consider liking, subscribing, and sharing to help us grow our channel. So today what I want to do is cover substitution in multiple integrals. And what I want to start out with is u-sub and see if we can generalize this into a calculus 3 idea. So for a u-sub we have the integral from 2 to 5 of x times x squared minus 4, that quantity being cubed, dx. And we know this can be represented as this image that we have that function x times the quantity x squared minus 4 cubed as this this fourth degree curve, and it's going to be integrated between 2 and 5. So it really represents that that area under the curve. So when we take this using a u-sub, I'm trying to simplify the integrand into something that is easily integrable. So the way we do this is we tend to use, the property of composition. So x squared minus 4 is going to be my u. And then what I can do is I can recover basically an x dx or a multiple of x dx from, that u. So the derivative of u or the differential of u is going to be du, which is going to be 2x dx. I don't have a 2x dx, I got an x dx. So we know I have to divide both sides by 2 or multiply both sides by a half. Now we also have to stuff the 2 and the 5 into that u substitution, because when we transfer this over, we know it's going to be in terms of u as opposed to in terms of x. So, evaluating 2 and 5, this now goes from 0 to 21. So we know that, this image here transfers to this image here. And really, these areas don't match exactly. The area underneath u squared and the area underneath the integrand we discussed. Really what this is half of this thing's area. And that's really done by, this half right here. So when I take this to calculus 3, we're going to see that, this number also kind of comes up, or at least an idea of this number comes up when we're substituting in calc 3 using an f of x, comma y into some other function f of u, comma v. So we're going to make multiple substitutions. And let me write this over here, and then you can kind of see what's going on. So here's the setup. When we take this to u-sub in like a calculus 1, we know we're taking advantage of composition that, f of g of x times g prime of x dx can be simplified to the integral of f of u du. Now this is kind of a perfect simplification because we have a g prime of x dx. Now over here it wasn't quite perfect because I didn't get a 2x dx, so I had to divide both sides by 2. So just kind of assuming if there was a 2 here, this would set up exactly. Now, we also know that the interval from a to b turns into the interval g of a to g of b. Now, when we do this in Calc 3, when we do multiple sub, this is going to be the iterated integral over r of f of x comma y dA or dx dy or dy dx. Fubini's theorem allows us to switch these if we need to. Is going to be equal to the double integral over a new region g, just like this is a new region here, of f of two functions that are going to be of u and v. So really this is going to be f of functions of u and v, multiplied by what's considered the magnitude of the Jacobian, du dv, or dv du, depending on how you set up this double integral. So really you can kind of see that your f of x comma y is going to become some kind of f of u comma v, or at least functions of u comma v, multiplied by the magnitude of the Jacobian, where the Jacobian really looks a heck of a lot like this piece right here. Notice that this piece is grabbed. This is du dx is equal to 2x. So therefore, du is going to be equal to 2x dx. So you can kind of see that same work over here with this. So really what happens here is this, this 1/2 that sits right here really can be related to the idea of this Jacobian, this possible stretch or squish that you need going from one to the other. So let me come up with an example. I'll show you how this works. So here's our example. We're going to evaluate the double integral over the region of the quantity x plus y times the sine of the quantity x minus y dA. Now we can see that this is not really integrable as it sits. I can't just do a simple u substitution, because a lot of times we like to say, well, u is going to be equal to this inside part, and then hopefully I can recover a du that's represented as the other piece of its expression. So I don't see that here. So what we're going to have to do in this case is try to make this more of a separable equation that, I'd like this thing just to be of one variable and then this thing to be of another different variable. So then I can, integrate this first, and then this second with respect to, you know, their two integrals. So let's make a substitution. Let's call say u equal to the first one and then v equal to the second one. So let's say u is going to be equal to x plus y, and that would make v equal to the sine of, x minus y. So now this is just going to be u sine of v, which means I can integrate these things separately, assuming that this is going to be, you know, du dv or dv du. So in order to do this, I also need to, you know, change this region of integration. So in order to do that, I need to, you know, solve this thing for x and y in terms of u and v. So let's do that. Let's solve. Let's solve this one for x. So basically, I pick one of them that is the easiest to solve. I tend to go after the right one for some reason, but you can go here first. It's just a system of equations. So solving for this for x, I have v plus y is going to be equal to x. Now plugging v plus y into here, we're going to have u is equal to v plus y plus y. Now I'm going to solve this thing for y, because I'm trying to do y in terms of u and v, and then also over here x in terms of u and v. So sending the y to the other side, u minus v is going to be equal to y plus y, which is equal to 2y. So that means y is going to be equal to u minus v over 2. Now back subbing into here, that means v plus u minus v all over 2 is equal to x. That's what y is equal to. I guess we can multiply everything by 2. So then this is 2u is going to be, 2u plus u minus v is going to be equal to 2x. Simplifying this, this is going to be 2v minus v, which is just going to be v. So u plus v is equal to 2x, or x is going to be equal to u plus v divided by 2. All right, so now I've recovered this in terms of x and y, because remember what we have to do is I can't just substitute for my integrand, I also have to substitute for my region. And that's what we're going to do here. Now that I know this is x and y, and I know these are going to be the bounds for this particular region, well, let's go ahead and look at R. It's not really required that you graph R, but I like to see, you know, what the region is going to turn into. So when we do this, I'm basically asking, what does this become? So what I know is we have y is equal to x for this one. It's going to look like so. And then y is equal to x minus 2, so it's going to be a little bit lower here. Then y is equal to negative x, which is going to look something like this. And then y is equal to negative x plus 1, so up a little bit. So what we're going to get is we're actually asking us to, well, it's asking us to integrate, you know, this function over, you know, over this diamond-shaped region. And really, this is going to turn into some g. So in order to do that, I'm going to have to plug these things in here and see what happens here. So y is equal to x. So what I know is y is going to be equal to u minus v all over 2 is equal to x, which is going to be equal to u plus v over 2. Multiplying both sides by 2, u minus v is going to be equal to u plus v. Now you can see this is linear, so you have to solve for you know, all the u's on one side, all the v's on the other side. Remember that u's are kind of acting as your independent variable, and v's are acting as your dependent variable. What I'm trying to say is this is x comma y, and then when I turn this into g, this is going to be u comma v. So I kind of acting in this position, this is acting in this position. So when I can, I will try to solve for v. So sending, let's say v to this side, I have minus 2v, and then sending the u over is going to be 0, so v is going to be equal to 0. Similar here, y is going to be equal to u minus v over 2 is going to be equal to x, which is u plus v over 2 minus 2. Multiplying everything by 2, we're going to have u minus v is going to be equal to u plus v minus 4. We can see that the u's are going to cancel again. So minus 2v is going to be equal to minus 4, so v is going to be equal to 2. Up here, y is going to be equal to u minus v over 2 is going to be equal to negative x, which is going to be u plus v all over 2. I'm going to put a parentheses there just to make sure I don't mess it up. So multiplying, actually let's distribute that through, then we'll multiply by 2. So this is going to be equal to minus u minus v, and these are, you know, both all over 2. Now when I multiply both sides by 2, the 2's are gonna disappear. And actually what I see now is that these v's are gonna go away because they have the same sign. So adding it to the side or this side's gonna cancel. So then now what I have is 2u is equal to 0 or u is equal to 0. And then finally up here, y is going to be equal to u minus v over 2 is going to be equal to negative u plus v over 2. Please fit, plus 1. Got it. So multiplying everything by 2 again, we're going to have u minus v is going to be equal to minus u minus v plus 2. Don't forget to multiply that by 2, just like this one. That's one of the common mistakes I see. So again, we can see that those v's are going to go away. Sending the u to the other side, 2u is going to be equal to 2, so u is going to be equal to 1. So what did that region turn into? So v's, which is going to be this axis, I have zeros, so they're going to look like so, 0, and then this is going to be at 2, so it's going to look like this. And then your u-axis, these are vertical, so this is going to be u is equal to 0. And then finally, u is equal to 1. So this diamond-shaped region turned into something that is very rectangular, so really easy to set up as far as its integration. So a lot of times I like to use a vertical scanner bar when I can, so I can see that it starts at 0, goes to 1 for the u's, and then for the v's, it's going to be 0 to 2. Now we also have to figure out its Jacobian. So remember that just like your u-substitution, you have to do your du. So doing our Jacobian, j of u comma v, is going to be the determinant of, well, remember this is going to be dx du, this is going to be dy, dx dv, and then this is going to be dy du, this is going to be dy dv. Now, if you notice this, like the first row is going to be, it's in terms of x's as your numerator. So these are going to be the dx's over. And then the bottom is going to be the dy's over. Now, the first column is going to be derivatives with respect to u's. And then over here, these are going to be derivatives with respect to v's. So you can see the x's here, y's here for the rows. And then for the columns, these are going to be the du's for the first column and the dv's for the second. All right, so let's set this up. Now, it might be easier if I say this is 1/2 u minus 1/2 v. And this is the same thing as 1/2 u plus 1/2 v. So we can see that they're partial derivatives. The derivative of u with respect to x with respect to u is going to be 1/2. The derivative of x with respect to v is going to be negative 1/2. The derivative of y with respect to u is going to be 1/2, and then the derivative of v with respect to the derivative of y with respect to v is going to be equal to 1/2. And multiplying, we're going to multiply the diagonals. So the main diagonal, 1/2 times 1/2. Minus the opposite diagonal is going to be negative 1/2 times 1/2. So what we're going to get here is 1/4 minus a minus 1/4, which is going to be equal to 2/4, which is going to spit out 1/2. So finally, we know that our substitution goes as follows. The double integral over the region of f of x comma y dA is going to become the double integral over g of really kind of your f of u comma v, well, functions of u and v functions, which become these of g of u comma v, h of u comma v, multiplied by the magnitude of the Jacobian dA as well. Now these are going to be in x and y's, these are going to be in u's and v's. All right, so setting this up, this is going to now be equal to the integral. Well, our new region goes from, let's scan this way. So I know that the u's are going to go from 0 to 1, so these are going to be your du's. And then the v's are also going to go from 0 to 2. 0 to 2, that's going to be dv. Now remember, you can choose the order you want through Fubini's theorem. Just make sure that you get your region correct. Now this is going to be substituting these into here. X plus y is going to be equal to u. X minus y is going to be equal to v. And then we have to multiply by the magnitude of 1/2. or the absolute value of 1/2. The absolute value of 1/2 is 1/2, so it's going to be redundant here. But if you do get a negative, you have to change its sign. So pulling out that 1/2, and then also integrating. So from 0 to 1, the integral of the sine of v with respect to v is going to be negative u cosine of v evaluated from 0 to 2 du. So plugging in v is equal to 0, and also subtracting when v is equal to 2, and then when v is equal to 0. So this is minus 1/2 the integral from 0 to 1 of u cosine of 2 minus u cosine of 0 du. This is equal to 1. Now also the cosine of 2 is a constant, so that I can just integrate both of these pieces. So this is going to be equal to negative 1/2. The integral of u is going to be u squared over 2. So this is u squared over 2 cosine of 2 minus u squared over 2 evaluated from 0 to 1. So minus 1/2. 1 squared over 2 cosine 2 minus 1 squared over 2 minus the evaluation of minus a minus 1/2 when you plug in 0. So 0 squared over 2 cosine 2 minus 0 squared over 2. And we can see that that second half is going to annihilate. So what we're going to get here is negative 1/2 times 1/2 is going to be minus 1/4 cosine of 2. Minus a half times minus a half is going to be plus 1/4. So again, if you like our videos, please consider liking, subscribing, and sharing. It really helps us grow the channel. Thank you.